This is the last problem from the packet. Noah Vale, adventure lover, physics fan, and all-around great guy, is out on a walk when he notices that his girlfriend, the youngest Miss Elementary, has been kidnapped by his arch-enemy, Rock Goddamn. He is holding the trussed-up Ella in a wagon at the top of a 200-meter-long hill that is 51.8 meters high. Rockcod releases the wagon, which has a mass of 10 kilograms, and Ella with her 50-kilogram mass, and they accelerate down the hill. There is a coefficient of friction between the wagon and the hill of 0.100. The problem, as shown in the diagram, is that there is a cliff only 100 meters away from the bottom of the hill. Can Noah stop the wagon and Ella before she falls to a very messy end? At the bottom of the hill, Noah leaps into the wagon, adding his 60-kilogram mass to the total. By dragging his feet, Noah can increase the coefficient of friction to 0.330. Will this be enough force to stop the wagon and keep their love alive, or will Noah and Ella be taking the plunge? I didn't draw the diagram because you do have the picture already in front of you, so let's just list what we're given and what we have to find. And it's going to be easier to split this up into two parts, so part 1 will be for the part down the hill, part 2 will be once they hit the flat surface. So given for part 1. In part 1, we know that the total distance the wagon is traveling is 200 meters. We know that the mass of the wagon plus Ella is 60 kilograms, so 50 plus 10 is 60 kilograms. And we know that the coefficient of friction is 0.100. We also know that they're starting from rest, so their V initial is going to be 0 meters per second. If you look at the hill, it tells us that it is 51.8 meters high, and we know that it's 200 meters long. So given the hypotenuse and the opposite, we can figure out what this angle of incline phi is. So the angle of incline would be inverse sine of 51.8 meters over 200 meters, which would give us a phi, or angle of incline, of 15.01 keeps on going degrees. Since that's the angle of incline and the angle we'll want to use is theta, 90 minus that number gives us 74.9 keeps on going degrees for theta. So a little bit of trig that you had to use. What we can find from part 1 that would be relevant would be acceleration and final velocity. So overall, what we're going to look for in part 1 is final velocity. In order to find final velocity, we're also going to need acceleration. Drawing the force diagram for part 1. So here's my surface. We've got the weight going straight down, the normal force, perpendicular to the surface, friction opposing the motion. Breaking apart Fg into Fgy and Fgx gives us this force diagram. Let's just ignore the contact force between the wheel and the wagon. It's going to complicate it too much and we don't have enough information to solve. So assuming let's ignore that contact force as the wheels are rolling down the hill. So assuming that they're just kind of sliding. From our force diagram, you can say that the net force equals right minus left, so this will be frictional force minus Fgx. You know that frictional force is equal to mu times the normal force, and we know that the normal force equals, from the force diagram, Fgy, which means that the frictional force would equal mu Fgy. So net force equals frictional force, mu, Fgy minus Fgx. Breaking each of these terms apart into their equations. F net is mass times acceleration equals mu. Fgy would be mg sine theta minus Fgx, which is mg cosine theta. All of my m's cancel, so the acceleration equals mu g sine theta minus g cosine theta. So acceleration equals my mu 0.1 times 9.8 meters per second squared. Sine of theta, theta was 74.9, keeps on going degrees, minus 9.8 meters per second squared times cosine of 74.9, keeps on going degrees. This will give me a negative 1.59, keeps on going meters per second squared. It makes sense that my acceleration is negative because they're accelerating to the left if you look at the hill as your surface. So this number should be negative. Once we have acceleration, we can figure out what her final velocity is, or the wagon and Ella's final velocity as they hit the flat part. You don't have time and you don't need it, so we want to use the no time equation. V final squared equals V initial squared plus 2a delta x. Starts from rest. V final squared equals 2 times negative 1.59, keeps on going, meters per second squared, times. My delta x would technically be negative because the displacement is to the left. So this would be times negative 200 meters. Multiplying these out, we get 636.6 meters squared per second squared for V final squared. Taking the square root, V final equals 25.23, keeps on going, meters per second. So in part 1, when they reach the bottom of the hill, they're going 25.23 meters per second. And that again would technically be a negative number since they're moving to the left. Let's now look at part 2. So given for part 2. We just found the final velocity for part 1, which will be the initial velocity for part 2. So this would be negative 25.2, keeps on going, meters per second. This delta x, they're traveling 100 meters to the left, would be negative 100 meters. And that's actually the maximum. So that's as far as they can go before falling off the cliff. We know that Noah jumps into the wagon, so the mass of the wagon plus Ella plus Noah is 60 plus 60 kilograms. So the total mass is now 120 kilograms. By doing that, he changes the coefficient of friction to 0.330, and we know that they're going to have to come to a stop, so V final is 0 meters per second. What we're looking for here is how far they actually travel with Noah dragging his feet to try and get the wagon to stop. So for here, let's draw a force diagram of what's happening. You've got the wagon rolling, but now it's on a flat surface. You've got friction opposing the motion, normal force going up, and gravitational force going down. And again, we're going to just assume that this whole wagon is sliding. We're going to ignore the fact that those wheels are turning. So my net force is equal to the frictional force. This force diagram is a lot simpler. So looking at the force diagram, you know that Fn is equal to Fg. And knowing that frictional force equals mu Fn, we know that frictional force equals mu Fg. So net force, because it's equal to frictional force, will equal mu Fg. F net equals ma. This equals mu mg. So the acceleration is just equal to mu g. This equals 0.330 times 9.8 meters per second squared. Multiplying those together, we're going to get 3.234 meters per second squared. And this number will be positive because they're slowing down in the negative direction. So given acceleration, we know the initial velocity and we know the final velocity. We can find delta x again by using the no time equation. So V final squared equals V initial squared plus 2a delta x coming to rest at the end. So we have to see how far it's going to take them to come to rest. Negative V initial squared over 2a equals delta x. So this is negative negative 25.2 meters per second squared over 2 times 3.234 meters per second squared, equaling delta x. So squaring the top, dividing that by the bottom, we're going to end up with a negative 98.43, keeps on going, meters for delta x. Again, this is negative because they're traveling to the left. So it's going to take them 98 meters to come to a stop. They have 100 meters to do it. The question is, will this be enough force to stop the wagon? And the answer is yes. There's no rounding to do because it's not asking for a numerical answer. It's a yes or no question. So yes, this will be enough. This problem combined pretty much everything. You had angles, you had trig, you had kinematics, and you had Newton's second law. So this is a culmination of a whole bunch of things, which is why it's the last problem in the packet. Hopefully you were able to follow these steps. If not, feel free to ask me questions.